Ready to dive into some serious science. Today we're talking molecules evolving, get this, inside a computer. No lab coats necessary.
It's wild, right?
We're breaking down this fascinating research paper, and it's a mouthful. Graph-based molecular Pareto optimization.
Catchy, huh?
Definitely grabs your attention. But seriously, before we get lost in the jargon, can you set the scene for us? What's the old school way of doing this, and why does it even need an upgrade?
Okay, so imagine you're looking for like one specific grain of sand on a beach.
Talk about a needle in a haystack.
Basically, yeah. Traditional drug discovery was kind of like that. Scientists would have to create and test tons and tons of molecules in the lab, hoping to find that one with the exact properties they needed.
Sounds incredibly tedious.
Yeah.
And expensive.
Oh, it definitely was both. Now, AI and deep learning, those have shown some real promise for speeding things up, but they've got their own issues.
Like needing a supercomputer just to get started.
Exactly. Those deep learning models, they need huge amounts of data and a ton of computing power, which makes them out of reach for a lot of researchers. And that's where this new research comes in. It's pretty elegant. They're using something called graph-based genetic algorithms, and it's way more streamlined.
Genetic algorithms, is that where the whole evolving molecules thing comes in?
You got it. It's like evolution is happening on a computer.
Yeah.
But instead of, say, breeding faster cheetahs, we're breeding, well, better molecules.
Okay, I think I'm following.
So you start with a bunch of potential molecules, and then this algorithm steps in. And it's basically like breeding new generations of molecules. And the algorithm picks the ones that have the traits we're looking for, how well a molecule latches onto a target in the body, or even how easy it is to manufacture.
So instead of speed and strength, we're talking drug effectiveness, ease of production, that kind of thing.
You got it. And what makes this paper so exciting is that these algorithms, they're faster, they don't need as much data, and here's the kicker, they're open source. So now, cutting-edge research, it's available to a lot more scientists.
It's like democratizing scientific discovery, right? So instead of just a few big labs with tons of money running the show, now more researchers can get in on the action.
Absolutely. And that is huge for speeding up progress. I'm talking medicine, materials science, even renewable energy.
Wow. Now I'm really seeing the potential here. But you mentioned this Pareto idea earlier, and I have to admit, I'm a little, well, it's got me curious. What's so cool about that?
Pareto, yeah, that's where this goes from like really cool to like game-changing. It gets at a challenge we see a lot, not just in drug design.
Okay, yeah, you've got me hooked.
It's rare we're looking for just one, like the best solution.
Right.
Take a car, right? The fastest car isn't much use if it like guzzles gas and breaks down every 5 seconds.
Right, you'd want something with speed, fuel efficiency, reliability.
Exactly.
Yeah.
Same with molecules. A super effective drug is pointless if it's crazy toxic.
Yeah.
We got to think about efficacy, safety, how easy it is to make, how well the body absorbs it, so many things.
Well, so how do you even start to figure out the best option with all those things going on?
The Pareto front. Imagine a graph, right? Each point on it is a different molecule. Some might be super effective but have nasty side effects. Others really safe but not very effective. The Pareto front is like the outline of all the molecules that are the best possible balance of all the things we care about.
Instead of one winner, we get like a group of top contenders, each having their own pluses and minuses.
Right. And depending on what's most important in your situation, you can pick the molecule on the best spot on the Pareto front. Maybe you need a slightly less effective drug to significantly cut down on those bad side effects.
This makes a lot more sense now. It's not about finding one magic solution. It's more like mapping out the whole landscape of all the best possibilities so you can make a good choice. Kind of like having a treasure map, but instead of one X, it shows you every place that's got something good.
That's a great way to put it. And this paper compares two algorithms that are really good at finding that treasure landscape, NSGA-II and NSGA-III.
So they're like our high-tech metal detectors, helping us find those molecular treasures along the Pareto front. What's the difference between them? They both find the best solutions, right?
Yep, but they do it in different ways. Think of it like this. NSGA-II is like casting a wide net, trying to cover as much of the Pareto front as possible, really exploring a wide variety of those solutions.
So NSGA-III is like casting a wide net. What about NSGA-III? Does it take a more, I don't know, focused approach?
Exactly. Think of it like NSGA-III is more of a treasure hunt, but you've got a list of must-haves. Like we're giving it directions. We need a molecule that's super effective, has these specific safety things, and it's got to be easy to make. Go find the best options that check all those boxes.
So it's not just about finding A and Y solution on the Pareto front. It's about honing in on the ones that really matter for that specific challenge. Did they did they put these algorithms to the test? How do you know if they're actually any good at finding these molecular treasures?
Right, got to put them through their paces. They used a benchmark called guacamole. It's like, think of it like a training ground for these molecular design algorithms.
Like an obstacle course, but for molecules.
Yeah, exactly. And they focused on tasks where you're trying to improve existing drugs. So say you've got a drug that's already FDA approved. You want to tweak its structure, make it even more effective, or maybe reduce side effects. But you got to keep it similar to the original.
So the bar is already pretty high. They're not starting from scratch. They have to make something good even better.
You got it. And they tested them on real-world drugs. One was fexofenadine. It's an antihistamine. They wanted to tweak it to improve its properties while still keeping it similar. It's like a perfect example of multi-objective optimization.
You don't want to completely reinvent the wheel, right? Just make it, I don't know, smoother, faster, more efficient.
Exactly. And to measure how well the algorithms did, they used this metric called dominated hypervolume. It's basically a way to quantify how well they map out all those optimal options on the Pareto front, all those trade-offs.
Okay, so bigger, dominated hypervolume, better map, more potential treasure to pick from.
That's it. And the results? Both NSGA-III and NSGA-III, they outperform the traditional approaches. It's like having a superpower for designing molecules. But NSGA-III, it often did it more efficiently, used fewer computational resources.
So not just about finding the solution, but finding it in a way that's faster and doesn't need a supercomputer. That's huge for making this research more accessible.
It's a game changer, for sure. And, there was another really interesting thing they found.
Oh, listen.
They discovered that algorithms that kind of encourage some similarity in their solutions, so not just searching for the most diverse options, those actually did better at multi-objective optimization.
Really? That seems kind of counterintuitive.
It does. But it shows how important it is to find that balance.
Not just casting the widest net, but finding those sweet spots where innovation meets efficiency. This whole thing, using algorithms to map out the best options, it feels bigger than just drug design.
I know what you mean. Makes you think, what other complex problems can we tackle with this? Optimizing traffic in cities, designing better renewable energy systems, even tackling climate change. The possibilities are, really exciting.
It's like we're getting a glimpse into the future of problem solving. We can use algorithms to help us navigate all that complexity and make smarter decisions. It's not always about the right answer, but about understanding the trade-offs and choosing the best path forward.
I completely agree. And it's a future I'm excited to be a part of.
Me too. And to everyone listening, if this deep dive sparked your curiosity, keep exploring. Who knows what other Pareto fronts are out there just waiting to be discovered. Until next time, keep those brains buzzing.